This is a computer which is full of abstractions, and each layer hides history beneath it. And today we are going to peel back those layers one by one. And let's start from the first beginning layer, which is the outermost shell of the computer, which is abstracted for real users or for the direct users of the computer. Now let's look this. Now look this. This is the real physical part of your computers, but most users don't have to care any of this. I mean, we have got this fan here, we have RAM, we have CPU, we have hard disk, the motherboard, and more things. Inside this are concerned by the technicians, not the real users. The real users only concerned about whether the keyboard is working or whether the keyboard is working or not, or the CPU and other things. But these parts are concerned by the technicians, other users, not the computer users, instead of the technicians. So they need have to know about the circuit or the current flow of how much current is following this circuit, or how much voltage is required for this circuit, or for this circuit, or for this fan, or for any of components present here. You have to analyze this the currents, and what's the direction of the current, or the direction of current flow, and more things you have to know about these things. But this is only for the technicians. But there is other deep layer which is beyond the technicians, which will be concerned, or which the technicians don't give any care about, the second layer, which is only cared by the computer engineers or the computer scientists who has discovered these components. So whenever technicians see any error here, he don't have to fix it. Rather, he throw it and use other components so that he will fix it, because this is abstracted from here or from his knowledge. You don't have to know what is beneath it. But today I am also going toward to this inside, what is really happening in this side, also in the CPU. I'm going to discover or peel back to inside what is really behind these things, these RAMs and the CPUs. And if I have time, I may also talk about the hard disk or fan or any component. Or if you need any component, you need to have to the implementation of those components to know. Let me know in the comment section. I will, as much as I can, I will prepare the video for that. But for this channel or for this series, I'm going to deep go to this layer and the CPU components. So these components and the CPU is the building block, or the most tiniest, or the building block of this CPU and this RAM is transistor, not this or this, but the around, I think, 2 up to 5 nanometer smallest tiny part of this component that makes the digital, or what can we say, the computer logic gates that will be built on top of that. So from the transistors we will come up logic gateway with when we build the CPU or RAMs, and CPU and RAM will form a computer. So the most deepest, or the basic building block of any computer is a transistor. So which is around 2 to 5 nanometers small, which is 100 times smaller than smaller than viruses, or even it is much smaller than wavelengths. That's why we can't even see with normal microscopes, which we call it light microscope. Rather, we can only see using electrons microscope. So what is really transistor? So let me show you. When you have a wire that's flowing a current, and when you put here a breaker, well, you build the first concept of a transistor. What is transistor? Transistor inside the computers which with the building block of any CPU or any computing logic logic gateways are transistors. So this one, although you build the concept of transistor by putting a switch inside the circuit, but that is only, I mean, it needs a manual interaction to make it on or off. To follow the current from this to this, you have to manually press the switch or whatever we call it. But that's really in size, it will be almost what can I say to you, almost 5 centimeter, and it will be big. So to have that much big, it will cost us a lot of energy, a lot of space, and that's not be efficient for our case to build that transistor. So the first approach was that, but the earliest computers with built the vacuum tube. If you know, you can search it, the vacuum tube, which was around, I think so, 20 centimeters. It looks like this much. And that was also, even though there is no uh, any manual intervention to switch to make it on and off, but it has it's the size is big, and it is very large, energy consuming, and much more problems. So the brilliant scientist, I don't know with his name is, sorry for that, but he designed the tiniest or the molecular level transistor. The building block of computers is a transistor, as I said to you, and that transistor is around 2 to 5 nanometers in size, which is very small. But let's make it zoom, and it will look like probably like this, and it will have three terminals, which is this one is the base, and this one is the collector, and this one is the emitter. So the collector will continuously supply a current flow for this component, and this component will be transfer the current to this emitter, depends on this little current supply, which by applying a small current from this base terminal, the current flow from the collector to emitter will be allowed. So this will make the simple gate, which is where when the input is 1, the output is 1, and when the input is 0 and the output is 0. This is the simple gate of the computer. But we need more complex one. I mean, more or the more uh, thing that can do. So what else we can do having this uh, transistor? So, and I said to you, this big transistor is about, it's 2 to 5 nanometers. Very small. Imagine it is 100 times smaller than even virus. So you have to imagine. Don't forget that I will continuously telling you that it is very small. So let's go to the next layer. What else we can do. So if we put two transistors in parallel, look, we have two transistors in parallel where it will have a continuous supply current from the collector, and this is the emitter, and this is the bases, which we have two bases. So according to, if we give 0 and 0, that means the current will not flow, so the output will be 0. And if we supply 1 from one side but 0 from this side, even though the current flows until this, but it will not flow from this, so it will generate 0. And even if we flip it, and when we put this one 0 and this one is 1, I mean a current, when we apply current from this, but we didn't apply from this, the current will not flow, that which represents 0. And this is the, if you remember, the AND gate. Congratulations, we have built the first complex gate, which is called AND gate. So, but this, when we look at this, will be very strong, right? It look like complex thing. But what if we use the power of abstraction? Let's abstract this thing, this inside thing, by making, in every gate we have etc. So let's get rid of that because we don't have to consider it. There always, but remember there is always a current supply from the collector. So when we put these two transistors in parallel and get rid of them, and we have two pins. So let me make it perfect for you. Let's abstract it. So when we abstract it, we get this, which is when we give it 1 and 0, the output will be 0, 1, and 0 and 1, which will be also 0, and 1 and 1. The only case that the output uh, will be 1 is when both are 1, when both are uh, supplied a little current from this and this terminal. That is the first gate that we use in the processor, or even in much complex in our RAMs also. So what will be the next? The next will be OR gate. So who is going to be the perfect one who will design the OR gate? And drop down in the comment section. I will explain in the next part video. Thanks for watching my video, and if there is any question, you can ask me as much as I can. I will help you understand this.